Hello there. Welcome to Chapter 4, Section 3, as we're going to begin looking at more patterns and these things called nonlinear functions, as well as linear functions. You'll need to be able to work with both. But to get started here, and you should have this template in front of you, and we're going to jump right in with a little review about just finding numbers in patterns. So take a look at the first one and see if you can figure out what number follows in the pattern there. 1, 2, 4, 8. And if you notice, it looks like it's doubling every time. So the next number there would be 16. Whereas with number 2, it goes from -8 to 4, 4 to -2. All right, so if you watch the pattern, the sign is changing each time, and hopefully you can see that the next number would be 1. It looks like it's dividing each time by -2. Or you could think multiplying by -1/2. And the third one there, that's an interesting one. See if you can figure that out. 1, 3, 9, 27. And the next one would be 81 there. So you might be thinking it multiplies by 3 each time. Another way you could think of it is 3 to the power of a number. The first number, 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. And 3 to the power of 4 is 81. And the fourth one right there, the top number is 1, it looks like, every time. And they're just doubling the numerator right there. So that's one way that you should be able to see patterns. And if you take a look at number 5, the next pattern in this shape would have how many? 16 blocks. We've got 1, 4, 9. The next one would be 16, and these are powers of 2 actually. Or you could just draw out the squares there and see that it would be 4 by 4, which would have a total of 16 blocks for you there. So that's kind of review information that you should be familiar with. A couple important words in this section right here. Linear. Linear, that review for you, that basically means if I were to graph it, it would make a straight line. Okay, it also means the rate of change is constant. That's really the mathematical piece that we'll be looking at later. The rate of change is constant. And then nonlinear then would be not a straight line. Okay, not a straight line. And I'll change to red here. And nonlinear, the rate of change varies. In other words, it's not the same all the way through the graph. Okay, so if you have any part of a graph that is not a straight line or doesn't have a constant rate of change, it would be nonlinear. Maybe it helps to take a look at number 6 where you can really see what's going on here. It says circle the graph that is nonlinear, or there could be more than one. So if I take a look at number 6, that makes a straight line, the graph right here. So this is linear. Okay, but if we take a look at number, or the middle one here, we see right here that it's no longer a straight line, so that's non-linear. So according to the directions, it said to circle the one that's nonlinear, so that would have a circle around it, as well as the next one would also have a circle around it because that's not linear. However, the last one is linear because the straight line is right there, right above the line I just drew. So that is linear right there. Okay, so linear, nonlinear, definitely going to need to know those words, and yeah, we'll go from there. So linear versus nonlinear. Let's take a look at problem number 1 here, where it says classifying functions as linear or nonlinear. You're going to need to be able to work with a table or graph or an equation to figure out if it's linear or not. And what they're doing here is they're taking a look at, let's say you take a piece of paper and you cut it in half. And they just said cut it in half n number of times. That means you cut it in half. Oh, you cut it in half once, you turn it, cut in half again. You keep doing that over and over and over. It says, is the function linear or non-linear? And what they're doing is they're comparing the number of cuts you make versus the fraction of the original. So if you make one cut, you'd have 1 out of 2, or half. And then if you make a second cut, in other words, if you cut that half in half, you'd have 1/4. And then if you cut that half in half, you've had an eighth and 16th, etc., etc. So it says we're going to figure out if this is linear or nonlinear by graphing the function, which is what they're asking here to do. So the first thing is recognize that these are ordered pairs, okay? Where 1, that's in from here, that's the number of cuts, okay? And then that's kind of like x. And then the y value, that's a, which represents the original area remaining. Okay, so 1 cut leaves half the original. 2 cuts leaves 1/4 of the original. 3 cuts leaves an 1/8 of the original, and on we go. So then it asks you to plot the points. And notice that the graph on your paper is cut up like this. Clever what they did with the scale here. They counted basically by eighths, or you see that's an eighth, that's a fourth, and that's a half, and that's 3/4, and that's 1. So if we plot 1, 1/2, would you plot that right now? They've already done that for you, but you start at the origin, you go over 1 up to a half, would go right there. 2 1/4 would go 2 1/4 right there. Again, notice the axis is labeled, okay? Number of cuts and the fraction of the area remaining. These are our 2 variables. Remember that this one is the independent, and this is the dependent variable. Let's review from the last section. The area remaining depends on the number of cuts that you do. 3 cuts right here would give me 1/8, which would be right there, and then 4 cuts would be half that. And it would continue going closer and closer to the x-axis, or the n-axis in this case. But you think about it, it's never literally going to touch that x-axis, even though they would get so small we wouldn't be able to actually continue to cut it. But it says complete this sentence. Is this linear or nonlinear? And the answer is it's nonlinear, because right here you can see that the graph starts to curve. Okay, and it gets closer and closer. So this is not a straight line. So this is a nonlinear function. Nonlinear function. Now there are other things we can do with the table. We could figure it out by seeing that the amount of area is not constant every time you make a cut, which would show us that it's not linear as well. Okay, moving on down to number 10, it says, will the area A in exercise ever reach 0? Well, technically no. But like I said, it would get so small we wouldn't be able to cut it. Technically you can't. If you cut something in half, you have something remaining, though it might be too small for us to measure. The literal answer for 10 would be no. Okay, why? Well, take a minute and write your own explanation. But every time you cut the paper in half, it gets closer to 0, but it never entirely disappears. So you can write that explanation on your paper there. That's the bottom of page 119. Moving on to the next page. Make sure you're hitting pause as you go so you can think about and get all the information down here. Well, let's take a look at this interesting relationship, this function. It says, let's say that they're drawing this figure that they have sketched out here. It kind of looks like a tree where it comes out, you have 1, and then it sprouts out into 3, and then each of those sprout out into 3, and then each of those sprout out into 3. It says, the table shows the number of new branches in each figure of the pattern below. What is a pattern you can use to complete the table and represent the relationship in words, equation, and graph? Okay, so on the first figure 1, there were 3 new branches. See, that's figure 1, and it's got 1, 2, 3. All right, in figure 2, there's 9. You see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 new branches. And in the third one was 27. So they're wanting to know what would happen if you continued that pattern. Well, let's come back to that in a moment. Okay, it says describe the pattern, and there's several ways you could say that. One way would be that the number of new branches is 3 times the number of the previous new branches. Okay, so it's 3 times that. In other words, they're taking that and they're multiplying it by 3 every time, and that actually would work just fine for us. But I'd like you to notice, be able to see it in this other way. I mentioned this in a previous problem. You could also realize that the number of, fill in right here, the number of new branches is equal to 3, that's to the power of the number of the figure. Okay, so if we could write it like x and y, we could turn that into a math equation because this is 3 to the power of 1. Okay, the 9 is 3 to the power of 2. 27 is 3 to the power of 3. So we could actually write that function as the equation y equals 3 to the x. So if I asked you to fill in if x is 4, we could say that y is equal to, equal to 3 to the power of 4, which is 81. Okay, this one y is equal to 3 to the power of 5, which is 243. So that's another way that we could write that function to that problem. And then if we were going to graph it, you can go ahead and hit pause here because I am going to have to stop my video. You can hit pause here and fill those out and fill in your graph based on those data right there, and then we will pick up with the next video.